So I'm going to turn the floor over to Hagen to talk to us about grid to ground, what GISers like us need to know. Thanks for doing the presentation, Hagen.
Yeah, absolutely. Yeah, thank you guys for your patience. Sorry about the excitement there. So Keith already introduced me, but just in summary, my name's Hagen Beckstead. I work here at the GIS Training and Research Center as the geodetic analyst. I'm also a licensed surveyor here in the state of Idaho, and I'm the editor of the Idaho Society of Professional Land Surveyors publication, the Gem State Surveyor. Little personal detail, I also think of myself as a chronic DIYer. One of my foundational philosophies on life is, you know, why buy something for $10 when you can make it yourself for 100? My wife sometimes disagrees, but I'm afraid I'm stuck that way. So I want to talk to you about grid on ground, what GISers need to know. My career as a professional land surveyor has kept me in close contact with GIS professionals throughout the years, mostly in terms of providing geodetic and cadastral control coordinates for GIS applications. And hopefully that has given me some insight into how this all works and what information we all need to be aware of, and hopefully will be useful to you. So for this presentation, I'm going to be focusing on official grid coordinate systems. In particular, I'm going to be looking at state plane coordinate systems. Surveyors often use arbitrary coordinate systems for their own convenience, but for GISers in the United States, the majority of grid to ground conversions that you're going to see will involve state plane coordinate systems. So although we are going to be looking at this in more detail, I want to point out right from the start, it's important to recognize that grid coordinates are computed. We don't measure them. And specifically, they are computed from a reference datum. So for example, in the case of state plane SPCS 27 coordinates, those are going to be computed from the latitudes and longitudes of the North American datum of 1927. In the case of SPCS 83 coordinates, those are going to be computed from the latitudes and longitudes of the North American datum of 1983. Maybe the first question we need to ask ourselves is, why do we use grid coordinates at all? Why do this in the first place? It's a little strange if you think about it that we take surveyed distances, surveyed locations on the surface of the Earth. We reduce those to latitudes and longitudes on some reference ellipsoid, and then we reduce those down to grid and work with grid coordinates that then we have to scale back up to surveyed distances. It seems kind of strange that it's almost like we're working in a circle, coming down from the surveyed data to the grid and then trying to get back up to the surveyed data. Because the fact is that none of us lives on the grid. We're all living off of the grid up here on the topographical surface, as a geodesist might call it. And because we do that, we have to go through this conversion process of getting back from the grid to the topographical surface. That's the foundational problem of the grid to ground conversions. So why do it? And the answer is that we all want the Earth to be flat. It would be much easier for us to work with our spatial data if the Earth were flat. Unfortunately for us, except for Florida, it's really not flat. Most of the Earth is covered with pretty, big significant changes in relief in the topography, and the Earth itself is an oblate spheroid. So we have to work with large-scale measurements on the spheroid, but we also want to work with small-scale measurements on the grid, because spherical trigonometry is hard, and we want to create maps. Maps like this one. This south part of Idaho. This is just a classic example of how we take the round Earth and we, for various reasons, need to look at it in 2 dimensions on a plane. And even if we're working on simple problems, simple spatial problems like the distance from point A to point B, we have the difficulty of working on the surface of the curve and computing those things mathematically. It's just not easy. If you're looking at latitudes and longitudes and heights, it's really difficult to process that information and to see the spatial relationship the way that you can with regular geometry. By comparison, geometry is very easy. We all learn geometry from the time we're in junior high school, and we learn things like Pythagorean theorem. And so if we can use those geometric principles to compute things like bearings, distances, and areas, it's much more convenient for us to do so, and there's a much lower chance of error. We don't want to build a Walmart with latitudes and longitudes and be out trying to compute cuts and fills for stakes. If you're a surveyor, it's much easier if we can look at differences in how far north and how far east it is. But all good things come with a price, and the convenience that we get by working with grid coordinates comes with a price, and we lose accuracy. I don't want to delve too much into map projections, but this is a diagram that is probably familiar to many of you if you've had a class in map projections or cartography. You'll notice looking at this that there are 2 green circles where this flat plane called the developable surface intersects the ellipsoid surface. And this is what we are trying to do when we create a map. We want to project that round surface of the ellipsoid onto a flat plane. There are various methods that we use to do that, but they all have certain things in common. If you look at this one, you should notice that when you're looking at the area inside of the 2 points of intersection with the ellipsoid surface, the distance along the curve has to be longer than the distance along the plane. The curved surface is reduced or compressed in order to fit on the plane. But if you look on the outside of those 2 points of intersection, you find that the opposite is the case. Those distances along the ellipsoid have to be stretched in order to be projected up onto the plane. And because of this, we get what's called linear distortion. When we're working with coordinate systems in the standard state plane coordinate system zones, the NGS has designed those coordinate system zones to keep that error within certain thresholds. So the state plane coordinate system zones, for example, linear distortion was designed to be kept within 1 part in 10,000. And so 1 foot of error per 10,000 feet of measurement. But it's important to realize that linear distortion is not measured up here on the ground. That 1 part in 10,000 feet of error is measured on the ellipsoid. And that poses some issues for us in the surveying community where we like really precise measurements, because just like none of us lives on the grid, none of us lives on the ellipsoid either. For most places in the United States, all of Idaho, the topographical surface, the ground that we live on, is above the ellipsoid. And those same principles of linear distortion that we were talking about apply. You can see from this image that if the blue curve, which is the ellipsoid surface, is longer than the orange line between those 2 points of intersection, then the arc length along the purple curve is going to be even more so, because the purple curve representing the topographical surface is even farther removed from that plane. So at this point, it's important that we maybe look at our scale factors. When we are working with grid coordinates, we talk about scaling from grid to ground, but it's easy to forget that there are actually 3 different scale factors involved. The first scale factor is what we call the elevation factor, and that's based on our elevation or our height above the ellipsoid. To get from the topographical surface down to the ellipsoid, we have to compress those distances, and then to go from the surface of the ellipsoid down to the grid plane, we have to compress those again, and that's what we call the grid scale factor. The grid scale factor is the part of that transformation that moves us from the surface of the ellipsoid to the projection plane itself. The third part, well, let's actually look at this first. This is a depiction of that second scale factor, the grid scale factor. And you'll notice if you look at that point between the 2 intersection points again, the scale factor is less than 1. This is where that ellipsoid distance has to be multiplied by a factor less than 1 in order to compress it to the length of the line on the plane. And if you look to the outside of the points of intersection, the scale factor is greater than 1 because that ellipsoid surface has to be stretched to meet the plane. The only 2 points where the scale factor is 1, where ellipsoid distances are equal to the grid distances, is at those 2 points of intersection. Everywhere else we have linear distortion. If we combine those, the grid factor and the elevation factor, we get the third factor, the third scale, which is what we are normally talking about when we talk about scaling from grid to ground. This is the combination scale factor. And the combination scale factor allows us to move back and forth from the grid to the ground or topographical surface itself. So when we are dealing with state plane grid coordinates, we're working with projections that the NGS designed to be what is called conformal, meaning that the angular relationships between points are preserved for a small area. And so by scaling these coordinates from the grid back to the ground to get that linear distortion removed, in a map projection that preserves the angular relationship between the points, we kind of get the best of both worlds. It allows us to work with regular geometric principles, 2D geometry, but not have the linear distortion that comes with that initial conversion. So ground coordinates, when you're working with ground coordinates, as opposed to grid coordinates, there are a few questions that you need to ask yourself. First, what are ground coordinates? There is no state plane ground coordinate system. The state plane coordinate systems that you see in the library on your GIS are going to be grid coordinate systems. Those are going to be coordinate systems that have really the maximum amount of error because they're on the plane. And so there's really no standard ground coordinate system that you'll find, and there's no standards really guiding how surveyors scale their coordinates from grid to ground. So it's important to know a few things to store in your metadata. It's also, I think, important to have some practical knowledge of how surveyors actually work, so you can be aware of maybe potential pitfalls. None of us wants to end up like this guy. While the chances are admittedly slim that you'll end up in legal trouble for confusing grid and ground coordinates, you still can end up in trouble with your ground coordinates if you don't have the right metadata. So I can't look at all of the various ways that surveyors might do this scaling operation, but I want to look at a few examples that I think illustrate the problem and illustrate some of the concerns for GISers, and hopefully illustrate why the metadata is important, and maybe offer another suggestion for how to get around the problem. We're going to look at 3 examples. In the first example, these are all points in the Pocatello area. I'll show you in a Google Earth image in just a moment how these points are related to each other. But in the first example, we're going to look at one where a surveyor is scaling from a project location. We're going to look at one where the surveyor is scaling from a zone origin for our second example. And I think this is how a lot of people assume it is always done, but it's not. And then for the third example, we are going to look at one where the surveyor chooses to scale the coordinates from an origin of 0, 0, meaning that the northing is 0 and the easting is 0. Hopefully this will make more sense as we go through these. So this Google Earth image shows you where the points are located. As you'll see, point A is located on Idaho State University campus. Point B is somewhat north and east of campus. Point C is actually on Red Hill. For this example, the surveyor is scaling from point A, which would be the project location that he puts into his software. And he's doing that because point A is central to the other work that he's doing. It gives a good reference for all the other points to be scaled from. You'll recall that the elevation factor in our combination factor is based on your height above the ellipsoid. And so if you're working in an area that has, fairly consistent elevation, usually what you want to do is you want to pick a point in your project that is more or less representative, kind of a midpoint for the whole project to use for your scale factor. That's what the surveyor in this case has done. So you'll notice these are the grid coordinates for point A, point B, and point C. All of these are in just standard state plane grid Idaho East zone. Those are the grid coordinates, and then at the bottom there, I've run through just the normal coordinate geometry to show the lengths of the lines in grid distances. When the surveyor set his project location from point A, you'll notice that point A, the grid coordinates and the ground coordinates remain the same. They don't change. However, points B and C, you'll notice that the grid coordinates are different than the ground coordinates. And there at the bottom, I've run through the same COGO routine to identify what the lengths of these lines are in ground distances. If we compare those, the differences between the grid distance, the measured or computed ground distance and grid distance, line A to B is on the low end. That's our closest. We have a difference of 1.17 feet in that measured line. For a surveyor, that's a pretty big deal. Well, for a lot of people, we want our ground measurements to be much closer than that. Line B to C is the longest line, and so it has the greatest distortion, and the difference between grid and ground distances there is over 2 feet. With the scale factor at our location of 1.0002633, so on, the coordinates will change by 0.263 feet per every 1,000 feet. Points B and C also, because it's scaled from point A, points B and C will appear to shift or move away from point A in the direction of the red arrows. And there are a variety of reasons why a surveyor may or may not want to use a method like that. One reason he might want to is his ground coordinates are close to, he wants to keep his ground coordinates close to true state plane coordinates. For example, if he's overlaying aerial imagery on them. But the downside to that is for a GISer, that those ground coordinates which have been scaled will appear to be very close to true state plane coordinates, which have not been scaled. And you may or may not be able to tell the difference. At short distances, you really won't be able to tell the difference. The other downside for another surveyor as well as a GISer is unless you know where the surveyor has scaled that from and what his scale factor is, you won't be able to take his ground coordinates and easily move those back to grid. In example 2, the surveyor is scaling from the zone origin. In Pocatello, the zone origin is south and east of ISU campus. So when the surveyor scales here, just think to yourself, which direction are the coordinates going to shift? You may think that coming from point A, moving south and east to the zone origin, that the coordinates will shift south and east, but that's actually not correct. If you compare, once you apply the scale factor and compare the coordinates, you'll see that the coordinates have shifted north and westerly. The ground distances remain the same because the scale factor is the same, but the shift in the coordinates is pretty significant. Computing the difference between our ground and grid coordinates, you'll see that they've shifted roughly 115 to 116 feet to the north and over 18 feet to the west. This should show up if you're looking at, if you have, say, a section corner and you have your section lines, PLSS lines in your GIS, you'll probably be able to detect this kind of shift. In the third example, actually, sorry, let me back up. A method like this might be used when the surveyor wants to have a consistent process where he's always scaling from the predictable point, in this case, always a zone origin. And one of the benefits to this is that the shift in the coordinates is usually significant enough that the ground coordinates can be identified and you can see the shift from grid. They're not as easily confused. In the third example, the surveyor chose to scale the coordinates from a northing of 0 and an easting of 0, which places the origin very far away, south and west of our project location. Because of that distance, when you multiply the scale factor, now remember about 0.263 feet per 1,000 feet. And when we're working with coordinates this large, when you multiply them by the scale factor, you'll get a substantial shift in the coordinates. Though again, you'll notice that the distance between the points, the ground distances between the points remains the same. So in this case, instead of 18 feet to the west, our coordinates are shifting about the same, 115 to 116 feet north and 154 feet to the east. It's pretty significant. It should show up on most maps. One reason why a surveyor might use that is because it's easy to go back and forth between grid and ground coordinates. All you have to do to go from grid to ground is multiply the coordinate by your scale factor, and then all you have to do to go backward is to inverse the scale factor and multiply your ground coordinates to get back onto grid. It is a convenient way for surveyors. I've seen a number of surveyors do this. Another advantage to it is that the coordinates are shifted significantly from true state plane coordinates again, and they're less likely to be confused. So those are 3 examples that I think illustrate hopefully a couple of the important points. The main things, I guess, the takeaways for GISers that I would point out are the scale factor is not the only thing that's important. You also want to keep track of where that origin is. If you need to be able to convert those coordinates back to grid, you're going to need to know the origin from where they were scaled, as well as the scale factor. And an additional thing, some surveyors apply what's called a false northing and a false easting. You need to know that kind of information in your metadata. So it's important to talk to the source and ask them, what exactly was your process for putting these coordinates on ground. The other thing that is important is, and I think this circumvents a lot of the problems, is if you can retain the latitudes, the longitudes, and the ellipsoid heights, the state plane coordinates can be computed from those. And so even if you have ground coordinates and you don't know how to shift those back, if you have the latitudes, longitudes, and heights, you can basically recreate the true state plane coordinates. Because latitudes, longitudes, and ellipsoid heights are more foundational, even though they're less convenient to work with, I think that is important information that we should store when we can. As for NatRef 2022, a lot of this is going to be changing with the new datums. It would probably be a good idea to update and talk about some of those changes when they occur. I will say one thing, and that is that the new state plane coordinate zones are going to circumvent a lot of this problem because they have been designed to keep the linear distortion to a minimum on the topographical surface rather than on the ellipsoid surface. So in a sense, the new state plane coordinate systems are already going to be scaled to ground. So hopefully after 2025, it'll be a lot easier to keep track of this and work with state plane coordinate systems and avoid some of the grid to ground conversion problems that present themselves. So sorry, we got a little late start, but if there's any questions, I would be happy to take them at this point.
Yeah, folks, if you have questions, feel free to either pop those into the chat line or unmute yourself and ask those questions. Now, I'll begin. I have a question for Hagen. I know that, as you already mentioned, NatRF 2022's grid, I think Dan Detterman called it a grid fixed or something like that, different type of grid. If here I am on the Idaho State University campus standing, let's say just outside my office, right outside of Gravely Hall by the Student Union building, if the grid were an actual tangible geographic feature and I wanted to see that grid or touch that grid, would I have to look up in the air? Would I have to dig down in the underground to find it, or would I be flat out standing on it?
So currently, you would have to look down in the ground very far. On Idaho State University campus, we're 4,000 some odd feet above the ellipsoid, and then the ellipsoid would be above the grid. When NatRef 2022 launches, it'll be a little different. I'm not sure the elevation of Gravely Hall, how that compares to where they've placed the grid on that projection, but we will still have some linear distortion. The grid will intersect various points of the topographical surface here in this part of Idaho. And so some areas will be above the grid, some areas will be below. And that's how they're keeping the distortion to a minimum by fitting the grid to the existing terrain. You're plus or minus. You have a little positive distortion and a little negative distortion, but none of it gets too far out of whack, the way it does currently with the grid being, far, far below us. Right.
Very good. Yeah, that's how I understood it when Dan Detterman was doing some presentations on this. So good information, helpful information for us to visualize and understand the coordinates that are underlying our GIS data. Anyone else have a question for Hagen